Hi there, I'm Andrew Flood from the University of Toronto, master's student there, and I'll be giving a quick overview of the research we're doing on bifacial silicon cells and novel reflectors that are both conductive and transparent in certain wavelengths as well. So, one of the problems with current reflectors, if you have, say, an aluminum reflector, is in bifacial cells, when you have illumination from both the front and the rear, you get no improvement from the rear illumination, obviously with aluminum or metals being opaque. So what we proposed as an alternative to that is a combination of ITO, which is indium tin oxide, and silicon nanoparticles. And when you have them together in bilayers, you get a highly reflective film. In addition, because we're using nanoparticles, which are porous, we get the indium tin oxide going throughout them, and we get a fully conductive film that we have on the back, and we can replace the aluminum contact completely. So two pathways, or two things that were done in order to assess whether this is a viable approach or offers any advantages, were optical simulations and also fabrication of a cell on a very thin silicon membrane. So in terms of simulations, we looked at a couple of cases and to compare to each other and see which might be the most advantageous in certain bifacial situations. So in particular, we considered silicon membrane with just aluminum reflector right on the silicon surface, an aluminum reflector with a silica intermediate layer as well, with an ITO intermediate layer, and also when we use selectively transparent and conductive photonic crystal, which is the reflector I was referring to before. Now the reason to use the intermediate layers is because we know these are optically preferable to, say, an aluminum reflector just on the back, but they can be more difficult to fabricate. So the results in terms of simulation were that, yes, when we take into account just illumination from the front, your aluminum reflectors, particularly the one with the silica intermediate layer, has a slightly better performance. But when we include rear illuminations, say about 10% of the solar spectrum from the rear, in addition to the 100% from the front, then the reflector on the back, so the photonic crystal on the back, is preferable, has a slightly improved performance. So in line with that, we thought, okay, next step, let's make one. Right, and see if we can fabricate it on a very thin silicon membrane. Because it's very difficult to handle silicon membranes, we start with a silicon on insulator wafer, which has a 10 micrometer layer, followed by silica, followed by a much thicker layer, and then etch away down to a smaller membrane. By doing this, we give ourselves room to actually handle the wafer with tweezers, which is pretty important when you want to go through the process. But this is something you just do in the lab. You would just use the whole thing being a 10 micron planar crystalline silicon in an actual fabrication industry format. So from there, what we do is we attach that membrane to a handle wafer to offer mechanical support while we go through the rest of the process. We use a combination of sputtering and spin coating in order to deposit the different bilayers, and then did a test to see whether we get the results we wanted. And we do see enhancement in the same regions we did in the simulations, and the same for both bifacial, so when we illuminate from the rear and when we illuminate from the front. The one thing of note that comes out of it is we have very high parasitic absorption at the short wavelengths in this reflector. So it inhibits the maximum performance we can get from rear illumination. In the end, going forward, what we plan on doing is creating a full cell. Hope to do that in the next few months, and then start playing with the other parameters to make it even better performing, such as ways to reduce that parasitic illumination. Thank you.
Now between the valence and conduction bands, you've got a forbidden gap. And if the gap you've got is just too wide, you'll lose your photons in a snap. Now if the gap you've got is far too narrow, you'll catch the whole darn fleet. But that won't do you any good, 'cause all you'll get is heat. Oh, solar energy, yes, solar energy. We can have our fun with the power from the sun using good old PV.